Our next speaker is Tom Rudelius from Berkeley, and we're very happy to hear him tell us something about dimensional reduction, asymptotic observables, and the Swampland program. So go ahead.
Great. So thank you very much to the organizers for the opportunity and the invitation to speak. My talk today will be primarily based on these three papers of mine, one from 2019 and two from earlier this year. A quick outline: I'm going to very briefly review the landscape in the swampland. I'm going to talk about asymptotic observables in quantum gravity, and I'm going to relate them to a new conjecture that I will define called the strong de Sitter conjecture. I'm going to give some lines of evidence for this conjecture. I'm going to suggest an alternative to the conjecture, and I'll end with some concluding remarks. So first of all, the big picture. I think the landscape in the swampland probably need no introduction at this point to this audience. The landscape consists of effective field theories, which can be consistently coupled to quantum gravity. And the goal of the whole swampland program is to delineate these from those in the swampland, which cannot be consistently coupled to quantum gravity. And we have a number of conjectured criteria for doing this. The weak gravity conjecture is one example. Says that you need, in any gauge theory, a super extremal particle, charge to mass ratio greater than or equal to that of an extremal black hole. We have the swampland distance conjecture, which says that when you go into asymptotic limits of scalar field space, you should have a tower of particles which become light exponentially quickly with increasing distance. We have the de Sitter conjectures, which place bounds on the gradient of the potential and the smallest eigenvalue of the Hessian, respectively, saying that the potential can't be too flat, or that the some flat direction should be sufficiently tachyonic. Now, unfortunately, there's this infamous trade-off, which has been discussed by many people in our field in previous talks, which is that conjectures that tend to be more rigorously established tend to be less interesting in terms of their consequences for phenomenology and cosmology. And on the other hand, conjectures which tend to be more interesting tend to be less rigorously established. And the de Sitter conjectures are really an example of this latter case. If true, these de Sitter conjectures would have enormous implications for how we understand our universe, dark energy, inflation, and so forth. But the evidence for them is rather tenuous. So they're true under the lamppost, but there's a high likelihood that there's a lamppost effect going on here. So we'd really like to understand when exactly we would expect these conjectures to hold true, what their regime of validity is. And in order to do this, I think it's crucial to first understand what the underlying physical motivation for these conjectures should be. And I think it's useful to contrast this here with the case of the weak gravity conjecture. So in the case of the weak gravity conjecture, we have a clear physical motivation, which is that black holes should be able to decay. Now, it isn't entirely clear why black holes must be able to decay, but it's perhaps a reasonable physical constraint to impose. It leads us to a bound, which seems to be true in all examples. And in particular, this bound has a sharp number here. This gamma is not some order 1 coefficient to be fixed later. It's some number that we know how to compute. For instance, in 4 dimensions, this is the square root of 2. The de Sitter conjectures, on the other hand, don't have such a clear underlying physical motivation. And relatedly, we don't have any sort of sharp bound here. We have these unknown order 1 coefficients to be determined later. So what we'd really like is some sort of physical motivation, sort of analogous to the principle that black holes must be able to decay, which is going to fix these coefficients and give us some clue as to when exactly we might expect this conjecture to hold true. So back in 2019, I made one proposal for what this might be, which is perhaps quantum gravity just doesn't allow for eternal inflation. If so, this translates into bounds on the gradient, the second derivative, and higher derivatives of the scalar field potential, which look fairly close to what we see in the de Sitter conjectures. Now, one key difference here, though, between this and the de Sitter conjecture bounds is this power of 3/2, as opposed to the first power, which appears in the de Sitter conjectures. So this is easier to satisfy than the de Sitter conjectures. So it's perfectly fine in string theory from what we can tell in many examples. But the fact that, at least in asymptotic regions of scalar field space in string theory, we seem to be satisfying a stronger bound than this, suggests that maybe there's some stronger motivation. So this led Alec Bedoya and Cameron Vafa to suggest what they call the Transplanckian censorship conjecture, basically the idea that subplanckian modes shouldn't stretch out and become larger than the horizon, and this gave them this bound in asymptotic regions of scalar field space. My goal for today is to introduce a third possibility. And in order to describe this possibility in more detail, I first need to tell you a little bit about asymptotic observables in quantum gravity. So the precise formulations of quantum gravity that we have are characterized by the presence of asymptotic observables that we know how to compute. So in anti-de Sitter space, for instance, asymptotic observables are given by correlation functions in the boundary CFT. In Minkowski space, we have an S matrix. But in de Sitter space and in cosmology, we do not have such precisely defined asymptotic observables. Part of the reason for this, why we don't have, say, an S matrix, is that in many cosmologies like our own, we have a Big Bang singularity. But there's an even deeper issue, which precludes the existence of asymptotic observables in an S matrix, which is the lack of asymptotic coldness. So in an FRW universe, you have a constant energy density along some Cauchy surface. And this means that if you just consider some finite region, the exterior of that region will have an infinite amount of energy and ostensibly an infinite amount of information. And that means that any observer at finite time who can only access a finite region in his or her past light cone can essentially say nothing about the global state of the universe. And this is really what makes it so hard to define asymptotic observables in cosmology. Now, it may be possible to sidestep this issue somewhat. Perhaps we can't define an S matrix, but perhaps there is still some notion of asymptotic observable that could be defined in cosmology. The prospects for this depend quite strongly on the particular cosmology in question. So I'm briefly going to consider today three possibilities: de Sitter space, which has an equation of state parameter of -1, universe governed by quintessence, also known as Q space, which has W between -1 and -1/3, and a decelerating universe, which has W greater than -1/3. So in the case of de Sitter space, an observer has this future horizon, which will prevent them from seeing all of future infinity. There's a finite entropy, which puts a limit on the complexity of any measurement apparatus, and therefore limits the precision of any would-be measurement. There's also a temperature, which may be very tiny in a universe like ours, which has a small Hubble parameter. But if one waits long enough, thermal fluctuations of arbitrarily high energy will occur and destroy any observers. So as a result, the prospects for observers and for observables in de Sitter space are not good. Things are a bit better in the case of Q space. So in Q space, a universe with quintessence, there is still this future horizon, which prevents an observer from seeing future infinity. There is still an entropy, and there's still a temperature, but the entropy here increases without bound in the limit as t goes to infinity. So at late times, there's no inherent limitation on the complexity of a measurement apparatus or the precision of a measurement. Similarly, the temperature goes to 0 fast enough so that high energy thermal fluctuations do not occur at late times and destroy observers. On the other hand, the only source of entropy comes from the thermal fluctuations of the horizon. So if one were to build a measuring device of arbitrarily high complexity, these thermal fluctuations would somehow need to be harnessed. And it's not entirely clear that that's possible. As a result, the prospects for asymptotic observables are okay. They're better than they are in de Sitter space, but they're not as good as they are in a decelerating universe. A decelerating universe has no future horizon, and it has infinite entropy available at late times. So in short, the prospects for exact asymptotic observables in a decelerating universe are as good as possible in a universe that still doesn't have asymptotic coldness. Now, at present, we don't have any precise formulation of such asymptotic observables. But it's conceivable, at least, that in order to define any sort of asymptotic observables in cosmology, we would need to have decelerating expansion at late times. So let us impose this requirement that we have decelerated expansion and study its consequences for scalar field potentials. So in particular, we're going to assume that the potential takes this exponential form, as is common to us in string theory, so that at late times, the field is rolling down this exponential. We can then describe the equation of state parameter in d dimensions in terms of this parameter lambda. And what we find is that w is greater than this value here, which is minus 1/3 in 4 dimensions, exactly when lambda is greater than this value here, 2 over the square root of d minus 2. And this is exactly the same condition as the strong energy condition, which is also exactly the same as the condition for decelerated expansion. So we see that decelerated expansion in this setup requires lambda to be larger than this value. So with this, I'm going to propose a novel form of the de Sitter conjecture, which I will subsequently try to motivate and argue for, which is the strong de Sitter conjecture. I call it the strong de Sitter conjecture because of its relationship with the strong energy condition. And the statement is that in asymptotic limits of scalar field space in quantum gravity, the strong energy condition should be satisfied. If the dominant contribution to the energy comes from some scalar field rolling down some exponential potential, then this is going to be equivalent to the condition that the gradient of the potential satisfies this expression here, which, as you can see, is a particular form. This is a particular coefficient for the de Sitter conjecture. Now note that this forbids accelerated expansion. So I must emphasize very strongly, this is not true everywhere in quantum gravity. It is violated even in our own universe. We can look out the window with a telescope. We'll see that the universe's expansion is accelerating. So this is definitely not true universally in string theory. But the claim here is that this may well be true in asymptotic limits of scalar field space, the same way that the Swampland distance conjecture is a statement about asymptotic limits of scalar field space. I'd also point out that this, if true, would tell us that the de Sitter conjecture can be thought of as a sort of weak gravity conjecture. The ordinary weak gravity conjecture says that when studying gauge theory coupled to gravity, we can effectively decouple gravity and just look at the gauge theory. The scalar weak gravity conjecture says that we can effectively couple gravity and look just at scalar field theory. In the case at hand, when the strong de Sitter conjecture is satisfied and we have a decelerating universe, the expansion of the universe can essentially be decoupled, so that at late times, we have a theory of just interacting objects in flat space. On the other hand, if this is not satisfied, so that we have a universe with quintessence, then gravitational expansion will continue to pull apart observers for all times. What does this mean for more realistic cosmologies? Well, if the strong de Sitter conjecture is true, then that means that any metastable de Sitter region must decay into a terminal vacua, which is either a crunching ADS region or into a decelerating hat region. Such a region is called a hat region because of the shape, this hat shape in the Penrose diagram that it makes. So this is a bubble here inside this metastable de Sitter region. This is a bubble of a decelerating universe. And the prospects for asymptotic observables in this region are similar to those of a decelerating universe. So again, as good as possible without asymptotic coldness. On the other hand, if the strong de Sitter conjecture is violated, the metastable de Sitter can also decay to Q space, a universe with quintessence. The prospects for asymptotic observables here are similar to those of Q space, and in particular, only finite entropy enters an observer's past light cone through classical evolution. Any other entropy must come from thermal fluctuations at the horizon. So what I've done so far is to propose a certain version of the de Sitter conjectures true in asymptotic regions of scalar field space. I've given you a physical motivation, but this is by no means a proof or really even a compelling argument. So what I want to do now is give 2 lines of evidence for why you might think that this is true in string theory. The first one is an old argument from Hellerman, Caliper, and Susskind way back in 2001. And the idea here is that we're going to suppose that we have some asymptotic region of scalar field space at which the theory asymptotes to a supersymmetric minimum in d dimensions. And what Townsend showed way back in the 80s is that the potential here can be written in terms of a superpotential like this. So if we want V to have this exponentially decaying behavior, then that means that W must also have this exponential decaying behavior. And when we plug this in and set V greater than 0, we learn that lambda has to be larger than 2 over the square root of D minus 2. So indeed, the strong de Sitter conjecture is satisfied in asymptotic regions of scalar field space that approach stable supersymmetric minima. And this is true in many examples in string theory. So we already learned just from this simple argument that in a very large class of examples in string theory, the strong de Sitter conjecture is going to be satisfied. The second argument that I want to give is an argument from dimensional reduction. So let's suppose that in big D dimensions, we have a scalar field theory coupled to gravity with this potential, and we're going to assume that we have a bound of this form on the potential. So this is sort of like the de Sitter conjecture bound, but we're going to allow this coefficient gamma to be unfixed, and we're going to let this coefficient C be unfixed. And what we want to do is to try to fix these by demanding that the bound should be preserved under dimensional reduction. So we reduce on a circle down to little d equals big D minus 1 dimensions. And what we find is that the bound will be exactly preserved if, first of all, gamma is equal to 1, which matches the de Sitter conjecture value of the exponent. But 2, this coefficient in D dimensions must be given by this expression here. And you'll note that if we set beta equals to 0, then this bound here is exactly the strong de Sitter conjecture bound. So what we learn here is that the strong de Sitter conjecture is exactly preserved under dimensional reduction. It will be satisfied in the higher dimensional theory if and only if it is satisfied in the lower dimensional theory after reduction. Now you might say, why is this a line of evidence in favor of the conjecture? Preservation under dimensional reduction isn't something that a priori we necessarily want to impose on a swampland conjecture. But the point is that this sort of reasoning has been used successfully in the past. So consider the case of the weak gravity conjecture. In D dimensions, we have a weak gravity bound of this form. The coefficient gamma can be written in terms of this coupling alpha and the dimensionality of the brane and space-time like so. And if we reduce this on a circle, we find that the weak gravity bound is exactly preserved. So the theory in lower dimensions will satisfy the weak gravity conjecture if and only if the higher dimensional theory satisfies the conjecture. Turning things around, this is saying that even if we didn't know what the right version of this coefficient gamma was, suppose that this gamma was unfixed, we didn't know what it was. Dimensional reduction is actually smart enough to tell us what the right value is, because if we demand preservation of the bound under dimensional reduction, we would actually be able to derive exactly the weak gravity conjecture. The same is true with the repulsive force conjecture, and so it's at least plausible that the same is true with the de Sitter conjecture. And we see here that if we imposed preservation under dimensional reduction as a consistency check, we automatically find the strong de Sitter conjecture bound. Let me make one last caveat here. There are a number of examples which have been noted to saturate the Transplanckian censorship conjecture bound. So see this paper by Andriot, Krabiori, and Erkinger for some of these examples. And you'll note that this coefficient here is smaller than the strong de Sitter conjecture value. So you might naively think that if we're saturating this bound, then we're violating this bound. And therefore that these examples may count as counterexamples to this conjecture. However, there's a subtlety here, which is that the examples that saturate this bound do so with respect to this quantity V prime, which is the derivative of the potential along a particular geodesic in scalar field space. The strong de Sitter conjecture, on the other hand, doesn't deal with V prime, it deals with nabla V, the gradient, which includes not only the derivative along a single scalar field direction, but also the contributions to the derivative, to the gradient, from derivatives with respect to other scalar fields in the theory. So it's at least conceivable that you could saturate this bound while still satisfying this bound. And in fact, there are examples in string theory, such as heterotic string theory compactified to 4 dimensions, which indeed saturate this bound along some directions in scalar field space, yet also satisfy this bound. So at present, we do not have a counterexample to this conjecture. Okay, so with my remaining few minutes here, let me suggest now an alternative possibility. So far, I've given this motivation for the strong de Sitter conjecture, the idea that the strong energy condition should be satisfied in asymptotic limits of scalar field space, and I've given you a couple of lines of evidence for this conjecture. Let's suppose now, though, that this conjecture is simply not true. Okay, so let's suppose that indeed it is possible to have quintessence in asymptotic regions of scalar field space. So far, right, we've supposed that exact asymptotic observables exist only in hat regions that have decelerating expansion. These are good candidates for observables because they have infinite entropy. But we saw that Q space does too. But in Q space, only a finite amount of entropy enters the observer's past light cone through classical evolution. So in order to get exact observables, to build a measurement apparatus of arbitrarily high complexity, we'd somehow need to harness the entropy coming from radiation. At late times, this radiation is going to consist only of massless particles because the temperature is getting smaller and smaller, unless there are some states whose energy tends to zero in late times. The existence of such states is exactly what's postulated by the Swampland distance conjecture. So let's make this more quantitative. Again, we suppose we have an exponentially decaying potential like this, and we'll suppose that we also have a tower of states satisfying the Swampland distance conjecture, whose masses scale like this with respect to its parameter alpha. So we find then that the emission probability of one of these particles is going to go like e to the minus 2 pi m times the apparent horizon. And if we plug in for the mass m in the apparent horizon, we find that this goes like e to the lambda over 2 minus alpha phi. So in particular, if alpha is greater than or equal to lambda over 2, then this probability will be constant or even grow at late times. And so the probability of emitting these particles will remain finite and remain bounded at late times, and therefore these particles will continue to be produced arbitrarily late into the future. So this is interesting because this bound, alpha greater than or equal to lambda over 2, was exactly a bound that's previously conjectured by Andrak, Cribiori, and Erkinger, where they compared the distance conjecture to the de Sitter conjectures. And so we see here that if we want for these Swampland distance conjecture states to be produced thermally at late times, that's exactly equivalent to the condition that was proposed by these authors. And therefore, the rationale for why this might be true in string theory might have something to do with this thermal radiation and its role in defining asymptotic observables in Q space. Okay, so let me end with some concluding remarks. We started out today by defining the strong de Sitter conjecture, which says that every asymptotic region of scalar field space should give rise to hat regions of decelerated expansion and satisfy the strong energy condition. These hat regions may be necessary for defining asymptotic observables in cosmology. So this is a physical motivation for why you might think this should be true. But then we also saw two more quantitative lines of evidence for this conjecture. One is that it's true in asymptotic limits where supersymmetry is restored. And the other is that the strong de Sitter conjecture is exactly preserved under dimensional reduction. I should also mention that dimensional reduction also selects certain forms of the ADS distance conjecture, the same way that it does with the strong de Sitter conjecture. I don't have time to talk about this, but I'll point you to my first paper from this year for more details. Finally, we considered this alternative possibility, which is that perhaps Q space does have asymptotic observables. And we argued that if so, the particles from the Swampland distance conjecture likely play an important role. So the big picture here is that we have considered these possible motivations for the de Sitter conjectures. Perhaps quantum gravity doesn't like eternal inflation. Perhaps quantum gravity doesn't like sub-Planckian modes being stretched larger than the horizon. But perhaps quantum gravity just doesn't like accelerated expansion in asymptotic limits of scalar field space. So obviously more work is needed to figure out which of these is the right version of the de Sitter conjecture, if any, and when exactly might it apply under what conditions in quantum gravity. We still don't know if asymptotic observables exist in cosmology. It's not totally obvious that such things must exist, but it would be nice if they did. If so, what are they? How are they computed? Is there a way to restore asymptotic coldness? And more generally, do our semi-classical descriptions of cosmology and eternal inflation need more serious revision? Finally, I think that the really big question, and sort of the main point of this talk, is to try to bring recent progress in semi-classical gravity, some of the exciting developments there, computations of the page curve, etc., into contact with some of the exciting developments that we've seen in our community in terms of work on the Swampland program. And what my work today shows, I think, is that there's some relationships between old works on semi-classical gravity, studies of asymptotic observables from the early 2000s, and more recent work on the distance conjecture, the de Sitter conjectures. And it would be nice to put these relationships on firmer footing. Thank you.
Okay, that was wonderful. Thank you. Let's all thank Tom. And then we'll open the floor for some questions. I see Thomas already has his hand up, so please go ahead.
Yep, thanks. Thanks, Tom. If I understood correctly, you're considering the possibility that in asymptotic field space, you cannot violate a strong energy condition. Is that correct? Mm-hmm. So if that's correct, I have a very simple, maybe I'm doing something wrong, but here's a possible counterexample. Just consider the exponential potential as you did, right? And I'm just assuming it's positive. And I don't care even about the slope of it, okay? Now, no matter where I am on this potential, no matter where in field space I am, what I can always do, I can put a scalar field and give it an initial push upward. And if I make the push very tiny, it doesn't go far. It will go up and it will return. And at the moment of return, there is always some transient form of acceleration. So the moment I have acceleration of the universe, I violate the strong energy condition. So I would say this shows that you can always violate a strong energy condition in asymptotic field space. The question is more, how much E-folds can you have? And I strongly believe there's some bound on the number of E-folds, but it's unlikely there seems to be a theorem against violating the strong energy condition in asymptotic regions.
Thanks. That's a good point. And perhaps I should reword exactly what I mean to say here, because I think you're right that such a thing could, for a finite period of time, a finite number of E-foldings, violate the conjecture. What you'll notice that my talk is sort of really motivated by this idea of trying to define asymptotic observables, which means that we're looking at asymptotically late times in the cosmological evolution. And in those examples, right, you have this finite period where you may violate it, but then ultimately at late times, you'll still have this decelerating phase. So it doesn't violate the spirit of the law, but that's a good point, and that one should be a little bit more careful in how this conjecture is stated. Thank you.
Thanks.
Okay, great. Do we have any more questions? I notice Eva has a comment in the chat. I don't know if you want to say anything about that. No, you're muted, Eva.
Yeah, I'm going to say the usual thing. You got to check anything you claim against existing models, and that includes the supercritical models. So I linked to one of the recent papers on that. And so in that context, the leading linear dilaton potential asymptotically is on the verge of accelerating, but not quite accelerating, but a little bit of what's called assisted inflation gets it accelerating. So it would be necessary to check any claim of this sort that way. And yeah, in general, these conjectures are, in my view, quite ill-founded, the ones about the slope of the potential, given what we've understood about de Sitter modeling. And I haven't seen objections to those models that are at all complete. I'm saying two things. One is, I would suggest checking your claim against, since you're talking about asymptotics, check it against the supercritical limit, which is the strongest leading potential in string theory. It's connected to other regions. This is understood by works of Hellerman and company, as well as those in our group. And it's obviously important. It's a leading positive term in the potential. So that's an elaboration on the comment in the chat.
Sure. Okay. Yeah. Yeah. So thanks for pointing me to those examples. I think actually this is good because it gives me a chance to explain something I want to stress, is that I am not of the opinion, certainly, that these sorts of bounds, say the strong de Sitter conjecture bound that I've proposed here, should be true universally in quantum gravity. My feeling is that we have examples where bounds of this form are satisfied, and the real goal should be to try to figure out what exactly is the domain of validity. So to me, the question is where exactly, why are certain bounds like this true in some asymptotic limits of scalar field space in string theory? And so to me, this doesn't by any means count as any sort of argument against de Sitter vacua in quantum gravity or anything like that. In fact, quite the contrary. I would say that if this is the right version of the de Sitter conjecture, then we know that it can't be have a completely universal domain of validity in quantum gravity, because we know that it's violated in our own universe. So I'd say the motivation here isn't trying to exclude de Sitter vacua from quantum gravity. The goal is to try to figure out where exactly and what exactly this form might be true. So I think, Eva, you bring up a good point, which is that maybe these not only are not perhaps only true in asymptotic limits of scalar field space in quantum gravity, but they're also not true in supercritical string models. So perhaps the domain of validity is even smaller than than I am proposing, and that's fine with me. To me, the real question is, what is the right domain of validity? Not trying to a priori argue it for one particular thing or another.
Okay, that makes sense. It might be good to stress that. I mean, I think the communication in the field is tends to be a little bit off in that regard. So okay, thanks.
Thanks. Yeah, I really did try to stress this when I talked about this being not true in our own universe. But yeah, I will continue to try to stress that.
No, but not true. I realize you're talking about asymptotics. That's why I brought up the particular example that I brought up.
Yeah.
So yeah, but even there, one has to be careful.
Sure. Thank you.
Okay, very good. These are certainly interesting questions, but I think it's now time to move on to our final speaker of the day.